I'll talk about the reducible and irreducible representation and introduction to the construction of the character table. Before that, let me introduce what is meant by a transformation matrix. Say, for example, I have a molecule, water. Let me assign the coordinates. This is Z, this is Y, and this is X. So the original coordinates are X, Y, and Z. Let me carry out the identity operation. So let me indicate identity operation as E. You know that identity is nothing but leaving it as it is. Don't do anything to the molecule. When you don't do anything to the molecule, XYZ will remain as XYZ itself. Now, I want to represent this identity operation E by a matrix. Let the matrix be 1 0 0 0 1 0 0 0 1. If we multiply this column, this row by this column by this row, you know matrix multiplication, I need not explain that. So what I do is, let me take this column, multiply by this row, x into 1 plus y into 0 plus z into 0, x. Then take this column, multiply by this row, x into 0, y into 1, z into 0, y, so on and so forth. So this is the transformation matrix for the identity operation. Similarly, I am going to find out the transformation matrices for all the operations. Say, for example, I am performing a C2 operation. C2 using z-axis as the axis. That means if I give a 180-degree rotation, x will go behind, it will become minus x, y will come this side, it will become minus y, and z will remain in the same position. So my final coordinates will be minus x, minus y, and z. So what will be the transformation matrix C2? So that when you multiply this matrix by this matrix, you should get minus x minus y z. So the matrix will be minus 1 0 0 0 minus 1 0 0 0 1. If you multiply, you will get that. Similarly, for sigma xz, I can write a transformation matrix. First of all, let us find out what happens when I do a sigma xz. A thumb rule is, if the plane is xz, x will remain the same, z will remain the same, y will become minus y. So my final coordinates will be, x will remain as x itself, y will become minus y, and z will remain as z itself. So the matrix for the sigma xz is 1 0 0 0 minus 1 0 0 0 1. This is the transformation matrix for sigma xz. Similarly, I can write the transformation matrix for sigma yz. Sigma yz means reflecting in this plane. So when I do so, x alone will become minus x, y and z will remain the same. And as I told you, if it is yz, nothing will happen to y, nothing will happen to z, x will become minus x. So I will write it as minus x, y, z. Obviously, the transformation matrix will be minus 1 0 0 0 1 0 0 0 1. So the four operations possible in water molecule is E, C2, sigma xz, and sigma yz. I have identified the transformation matrices for all the four. So let me write like this then. Namely, For water molecule, the E matrix is 1 0 0 0 1 0 0 0 1. For C2, the transformation matrix is Z is the axis. So minus 1 0 0 0 minus 1 0 0 0 1 is the transformation matrix for C2. And for sigma xz, the transformation matrix is nothing will happen to x, nothing will happen to z, y will become minus y. Therefore, 1 0 0 0 minus 1 0 0 0 1 is the transformation matrix for the sigma xz. And for sigma yz, as I told you, nothing will happen to y, nothing will happen to z, x will become minus x. So it will be minus 1 0 0 0 1 0 0 0 1. So this is the transformation matrix. So the correction of these matrices for the operations in a molecule is called a representation. Correction of matrices representing all the operations is called a representation. So these four matrices represent the molecule. Now I have assigned coordinate only to the oxygen atom. If I assign coordinates to all the three atoms, namely I assign coordinates to this. So my original coordinates are x1, y1, z1. x2, y2, z2, x3, y3, z3. These are my original coordinates. If I carry out an identity operation, nothing will happen to these coordinates, they will remain the same. So my final result is again x1, y1, z1, x2, y2, z2 and x3, y3, z3. So my transformation matrix for E will be a 9 by 9 matrix. I am not elaborating that for want of time. So I can write a 9 by 9 matrix for E, a 9 by 9 matrix for C2, a 9 by 9 for sigma xz and a 9 by 9 for sigma yz. Correction of these 9 by 9 matrices is a representation. Now, if the matrices are big, if they can be reduced to a smaller matrices by a process called block diagonalization, such a representation is called a reducible representation. If you have matrices which cannot be further reduced, it is called an irreducible representation. That's the information about reducible and irreducible representations. All that I want to say is, each operation can be represented by a matrix. Depending upon what you choose as a basis, the matrix can be smaller matrices or the matrices can be bigger matrices. If collection of bigger matrices are there, they can be reduced to smaller matrices. Therefore, these bigger matrices, collection of bigger matrices is called a reducible representation. If we have a collection of matrices which cannot be further reduced, that is called a irreducible representation. There can be any number of reducible representations for a molecule, depending upon what do you choose as the basis. But the number of irreducible representation is limited. You can't have any number of irreducible representations. What is the rule then? The rule says that how many classes are there in the molecule? how many classes of operations are present in a molecule? The molecule will have so many irreducible representations. For example, if I talk about water molecule, total number of operations is called an order denoted by H. What are the operations possible here? An identity operation, a C2 operation, a sigma xz operation, and a sigma yz operation. There are 4 operations. Total number of operations in a molecule, I said, is called an order denoted by the symbol H. And we talk about what is meant by a class. We have 2 planes of symmetry, sigma xz and sigma yz. By certain condition, you can prove that whether they belong to same type or not. Instead of using the term type, I will say class. Whether the 2 sigmas belong to the same class or not. That is done by a process called similarity transformation. So, by using the process as similarity transformation, you can find out whether these 2 sigmas belong to the same class or not. What is the similarity transformation? Let me consider I have 3 operations in a molecule A, B and C. Now, let me do these operations as, let me choose this C inverse A and C. If the result is B, this process is called the similarity transformation. If the result is B, then I will say A and B are conjugate to each other. A and B belong to the same class. This is the process called similarity transformation. I can find out whether the 2 sigmas in water molecule belong to the same class or not. What should I do? Let me choose sigma xz, carry out C2 inverse and then C2. The procedure is left justified. C2 inverse should be done first, then it is sigma xz, then it is C2. If your result is sigma yz, then we say sigma xz and sigma yz are conjugate to each other. They belong to the same class. Sigma yz is the similarity transformation of sigma xz by C2. Repeat the sentence. Sigma yz is a similarity transformation of sigma xz by C2. Or I said xz and yz are conjugate to each other or they belong to same class. Let me try and find out whether this rule is obeyed or not. If it obeys, then the 2 sigmas belong to same class. If it doesn't obey, each form a separate class. Okay, let me carry out that. Namely, I will take the water molecule. Let me put the C2 axis. Carry out C2 inverse. C2 inverse is nothing but rotating in the counterclockwise direction 180 degree. To identify what happens, I am labeling it as A and B. So, if this is the clockwise direction, C2 inverse will be anti-clockwise direction. If I do so, I will be getting B here and A here. I have done this. Then I am carrying out sigma xz. This is sigma xz. I reflect in this plane. What I get is A comes here and B comes here. I have done this also. Let me do C2 now. I am doing a C2 now. A clockwise rotation 180 degree. If I do so, B will be here and A will be here. Now I am going to compare whether the result is, if I do sigma yz, if I get this, then I will say xz and yz belong to the same class. Sigma yz means reflecting in this plane. If I reflect in this plane, A will remain in the same position, B will be in this position. But that is not so. It has exchanged. That means this condition is not obeyed. C2 inverse sigma xz and C2 is not equal to sigma yz. So the conclusion is sigma xz and sigma yz are not conjugate to each other. They don't belong to the same class. They belong to different classes. So in the case of water molecule, then I will say there are 4 operations I said, and the 4 operations are E, C2, sigma xz and sigma yz. The total number of operations is called the order I said. So order H equal to 4. How many classes are there? Just now we have found out the 2 sigmas do not belong to the same class, they belong to different classes. So E is a class, C2 is a class, sigma xz is a separate class and sigma yz is a separate class. So class is also equal to 4. Whatever is the number of classes in the molecule, so many irreducible representations will be there for the molecule. So water will have 4 irreducible representations. So this is done by this procedure. Whereas if you consider a molecule like ammonia, which belongs to C3V symmetry, the operations are identity operation, C31, C32, sigma, sigma prime and sigma double prime. Let me call this plane, the left plane as sigma. Let me call this as sigma prime and this as sigma double prime. If I reflect in this plane, I will call it sigma. If I reflect in the right plane, I will call it sigma double prime, and the central plane I will call it sigma prime. So totally there are 6 operations possible. An identity operation doing nothing, a C31 a 120 degree rotation, C32 a 240 degree rotation, sigma reflection in the left plane, sigma prime reflection in the central plane, and sigma double prime reflection in the right plane. So order is equal to 6. H is 6. Now I want to check whether these 2 belong to same class or not. You can only check like that. Operations of the same type, well, you can check whether they belong to same class or not. You can't check a sigma 3 C31 and sigma whether they belong to same class or not. Similarly, I will check up whether these 3 sigmas belong to the same class or not. Let me find out now. Say for example, I want to find out whether C31 and C32 belong to the same class or not. The procedure I said is similarity transformation. Namely, let me do a sigma inverse, a C3 and sigma. If the result is C32, then I will say C31 and C32 belong to the same class. Otherwise, we will say that they belong to separate classes. Let me perform the operation. This is the molecule. As I told you, again I label these atoms as A, B, C. And don't forget, the left plane is sigma, the central plane is sigma prime, and the right plane is sigma double prime. Okay, what is it I am going to do first? I said it is left justified, First I will do sigma inverse. So I reflect in this plane. If I do so, that will remain in the same position and C will come here and B will come here. I have performed sigma inverse. Let me carry out a C31 operation now, a 120-degree rotation. If I give a 120-degree rotation, C will go here, A will come here, and B will come here. So I will write it as C is here, A is here, and B is here. This is C31. I have done this, I have done this, I am going to do sigma now. Sigma I said is reflection in the left plane, in this plane. If I reflect, what I get is that will remain in the same position. A and B will exchange positions. Now let me compare. When will I get this from this? If I give a 240-degree rotation, for 120 A will go there, 240 it will come here. For 120 B will go there, for 240 it will come here. And 120 it will come here, for 240 it will go there. So this is equivalent to C32. So this condition is obeyed. C31 and C32 are conjugate to each other. They belong to same class. If they belong to same class, I need not write it as C31 and C32. I will write as 2C3. I mean there are two C3 operations. One is C31 and other is C32. Both of them belong to same class. Similarly, you can perform and verify that all the three sigmas are conjugate to each other, or the three sigmas belong to the same class. So in the case of ammonia molecule, which belongs to C3V symmetry, order equal to 6 and class equal to 3. I go back. I said a molecule can have any number of reducible representations, but the number of irreducible representations is limited. The total number of irreducible representations for a molecule is equal to the total number of classes of the molecule. So in the case of ammonia molecule, order is 6, classes are only 3. E is a class. The C31 and C32 belong to the same class. Sigma, sigma prime, sigma double prime belong to same class. So the number of classes is 3. So ammonia will have only 3 irreducible representations. Water will have 4 irreducible representations and ammonia will have only 3 irreducible representations.